Okay, hi guys. We are today going to begin talking about Chapter 10 in AP Statistics. So what we're going to do is we're going to start with Section 10.1. There's only two sections this chapter. The first section is proportions, and the second section is all averages. When we're working with these, this chapter is all about comparing two samples. All right, so last chapter we had, like, here's a sample, compare it to a number we decided ahead of time, right? The proportion of, I don't know, people who like chocolate ice cream the most is greater than 60%. And we came up with that 60%. Now what we're going to do is we're going to compare two different populations to each other and say, you know, are the proportions of the two populations the same or do they differ? So, for instance, now I could say, do children is the proportion of children who like chocolate ice cream the most equal to the proportion of adults who like chocolate ice cream the most? Or is the proportion of children going to be greater than the proportion of adults for liking chocolate ice cream the most? Right? One of the first things we need to talk about, clearly we're not going to just do the whole section today, but one of the first things we do need to talk about that's a biggie is what would the sampling distribution look like? So what would it look like if we took lots and lots and lots of samples of the same sample size, okay? If we had all the possible samples of the same sample size from a population and we drew the distribution of them. We did this back in Chapter 7 when we had a sampling distribution. So right here I've got the information for Chapter 7. Choose a simple random sample, okay? Then our mean of the sampling distribution we knew was the mean of p hat is equal to p. And then the standard deviation of p hat, the sampling distribution, was equal to, and here was our square root. Remember, this was q. Now what we're going to do is we're going to subtract. So we want the proportion from the first sample minus the proportion from the second sample. So this kind of ties in with like how we had to really think about with the paired t-test idea. Like, is it going to be positive? Is it going to be negative? You know, if the first number is smaller, then it becomes a negative value. If the first number is greater, it becomes a positive value, right? If they're exactly equal to each other, it's going to be equal to 0. So here are the key parts. If you're asked to describe the sampling distribution, which your textbook has a couple practice problems for that based on it as well. I'll tell you specifically what problems to do in class and when we do them. But when you've got that, then we know the shape. Here's the key, is that it's not just n times p, n times q. It's the first sample, n times p, n times q are greater than 10, and the second sample, n times p, n times q is greater than 10. So you have to make sure you catch both. Okay, if that's true, then your distribution is approximately normal. All right, we need to keep in mind that the center of the two subtracted is going to equal the population proportions of the two subtracted. You have to identify which way you're subtracting. It matters, right? If you do 1 minus 2 versus 2 minus 1, you might get, the opposite sign. So it's incredibly important that you always state, and we'll go through that when we do phantoms, of course. We have to state how we're going to be subtracting, okay? And then our standard deviation. Here's your formula for the standard deviation of a sampling distribution. So back here you see it was just, you only had one sample, so it was p times q over n. But here you have two samples. So inside one square root, it's p times q over n for the first sample plus p times q over n for the second sample. Make sure, a common mistake that I see students make is they break them into two square roots and add them together. And you have to make sure that you're doing it's two fractions added together inside the same square root. And you're allowed to use this, right? Standard deviations, we always need to check the 10% condition. But for this problem, you have to check the 10% condition for both samples. So you need to check, is your population at least 10 times your sample size for sample 1? And is your population at least 10 times your sample size for sample 2? So let's take a look at this first problem. All right, example 1, Nathan and Kyle both work for the DMV, but they live in different states. In Nathan's state, 80% of the registered cars are made by American manufacturers. In Kyle's state, only 60% of the registered cars are made by American manufacturers. Nathan selects a random sample from his state, and Kyle selects a random sample of 70 cars from his state. You don't have to have the same sample sizes. It's fine. We want to let, and so here they stated what we're trying to identify, right? We want to let P hat N minus P hat K be the difference in the sample proportion of cars made by American manufacturers. Now, when I jotted down mine, I wrote 1s and 2s, so it should be an N here, and you can make it an N and an N, and a K and a K. It doesn't really matter if you get to identify it on your own. If they tell you what to use, then you need to follow through with what they use. So, our shape of our distribution, okay? In order to figure out our shape, we need to check all of this, okay, back here with our shape. So you need to check all 4 of those, which I have done already. I used 1s and 2s, but here's Nathan. So you have 80 is greater than 10, good, 20 is greater than 10. Here's Kyle, the second sample. 42 is greater than 10, 28 is greater than 10, right? Make sure you have to use the right sample size. Nathan had 100, Kyle had 70, okay? Nathan's was 0.8, Kyle's was 0.6. Since all of these pass, then that means that we're good to go and our distribution is approximately normal, all right? To find the mean of your sampling distribution, part B, we're going to need to come back here and find the mean, right? And the mean of your sampling distribution is just P1 minus P2. So it absolutely matters. You have to do 1 minus 2, okay, or Nathan minus Kyle to get positive 0.20. If you went backwards, you would get this wrong because they specifically told you which way to subtract. All right, and then part 3, we want to find the standard deviation of your sampling distribution. So to do that, we need to first check, is our population at least 10 times our sample size for Nathan's state? Sorry, a little off the screen. And is our population at least 10 times our sample size for Kyle's state? Yes, right? We are going to have the number of cars, actually number of registered cars, right, in both states. So of course there's going to be more than 1,000 and more than 700 cars. So that lets us use this formula back up here for standard deviation. So you're going to have this guy for Nathan plus this guy for Kyle, right? P times Q over the appropriate N. Make sure you practice plugging it in. Got some old practice problems in there of other stuff, so we're going to do square root inside. We're going to do a fraction. We're going to do 0.8 times 0.2 over 100. If you click to the right, be very careful. Take a look. Do you see how my cursor is still inside the square root? You have to make sure that you're there. You want to hit plus, and you see how the square root above is extending now? And that's what you need. If you hit another fraction, you will see it's underneath, which is good. If you went right twice, it would have gone out of the square root and given you the other. So we're going to have 0.6 times 0.4 over 70. And then there's our answer. Okay, when you press enter, you can also confirm that your square root took the whole fraction and that you had 2 separate fractions. All right, and then that would be our standard deviation. Okay, so if a particular problem asks you to talk about the sampling distribution of 2 samples or 2 proportions being subtracted, then you would go through this process. All right, we're going to see this formula just like we did in chapter 7. All right, what we're going to do is we're going to talk now about confidence intervals. All right, and then we will hold off till the next lesson to do a full-blown hypothesis test. So when you're working on a confidence interval with a test of significance, okay, we need to be careful. We're going to, this is what's on your formula card. Okay, that's the formula card. Our statistic is our sampling distribution. It's p hat 1 minus p hat 2. You don't actually have to have this in parentheses, but I like to put in parentheses just to help us organize our work, because what's tricky is that your plus or minus goes here directly in front of the z star. Don't put the plus or minus here in between the p. This is always subtraction. And then whatever this answer is, plus or minus, these are the same 3 z stars we've had all along for proportions. 1.645, 1.96, 2.576, and so forth. Okay, and then you're going to do big square root. Be careful. back on the previous page, your sampling distribution, we had population proportions. So we had P and Q and P and Q. For a confidence interval, we don't know the population proportions. That's what we're trying to estimate. So since we don't know them, that's when all we can use is our P hat, Q hat. So those are those tiny details that you might want to make a note about. Okay. I copy pasted your conditions just right out of your textbook because it was an efficient way of getting all your information to you. We still have random. You just need to make sure that both samples are random, okay? We still have the 10% condition. Population is at least 10 times our sample size. You just have to check it for both populations, okay, or both samples. And then we're going to check N times P hat, N times Q hat, N times P hat, N times Q hat for all of them, okay? So if you guys read example 2, all right, we're going to have researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 elementary schools. A simple random sample of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, a simple random sample of 150 students include 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportion? We want to carry out a significance test using a confidence interval at the alpha equals 0.05 level to support your answer. So confidence interval at alpha equals 0.05 means 95% confidence, right? We know the process based on how much time we spend on this last chapter. We should be good to cruise. So I jotted down our information. School 1, I got here and here for my P hat and Q hat. School 2, I had 26 over 150, and then 0.1733 and 0.8267 for my P hat, Q hat for school 2. When you start, P is parameter, right? Well, how many population parameters do we have? 2. So we need to do both, all right? You're going to let P1 equal the true proportion of students at school 1 who did not eat breakfast. You're going to want to write tiny. I apologize. I did not give you quite enough space. So you're going to want to write small. In general, for me, I'm fine if you say let P2 equal, and then you can, it's going to be the same basic concept. You're just going to have to sub out whatever is the difference, right? So it's school 2. So I'm okay if you just put the quote marks to say like same as above, same as above, same as above, but it's school 2. All right. Now, our hypotheses. There are 2 readily accepted ways to write your hypotheses for these problems. All right, and it's both are okay. So you have to be comfortable with looking at both. You get to pick which one you want to write, but like multiple choice wise, you have to be able to look at both. So our hypotheses we've got are here. Okay, one way to write them is to say let P1 minus P2, right? So null hypothesis P1 minus P2 equals 0. Because if you're looking for the difference in the proportion, well, if you subtract them and it equals 0, that means they're not different. They're the same. Difference, and remember, confidence intervals have to be the same, like they have to be two-tailed tests. So the only way you can work with a confidence interval is if it's equal, not equal. But difference means isn't the same. So that's another key that it's not equal. So it's fine if you write, if you subtract them and it's not equal to 0, that means there is a difference. Well, sometimes people prefer to write them as P1 equals P2 and P1 doesn't equal P2. Mathematically, all we've done is we've taken this and we've added this to the right. We added this to both sides, P2 to both sides, so that disappears and it moves over there. And you've got that. So it's like whatever you prefer, right? Some people, this clicks a little better. Some people, this clicks a little better, right? You might want to write, this means that they're the same. This means there's a difference, right? Sometimes words really help you organize your thoughts as well. Okay, our assumptions, I acknowledge, are super annoying and tedious, and unfortunately they get worse later in chapter 12. Holy cow. But we'll get there, right? For now, we're just going to kind of cruise through. And I forgot my hats as I'm looking at this. So here are my assumptions. And you can't shortcut this any more than I already have, right? It's stated to be a simple random sample from both schools. Good, right? You got to make sure it's both schools. Large counts. I handled school 1, N times P hat, n times q hat, so I got 19 and 61. School 2, n times p hat, n times q hat, 26, 24, so we are good to go here. Okay, so large counts, we're good to proceed. Then we need to do our 10% condition. You need to check it for school 1 and you need to check it for school number 2. So school number 1, there are at least 800 students. School number 2, there's at least 1,500 students. Now, you guys might be, based on our area, right? You're like, there's not 1,500 kids in an elementary school, but the problem told us there is. So up here, the problem said more than 1,500 students attend each school. And that is critical to make sure that we pass the test. Okay. Our name is a 2-sample z-interval for proportions. We've been working with 1-sample intervals. Now we're doing 2 samples. We're comparing school 1 to school 2. The interval is here. You're going to have p hat 1 minus p hat 2 plus or minus z star big square root, and it's p hat 1, q hat 1, n 1 plus p hat 2, q hat 2, n 2. And yeah, you're going to type this in one big shot. So my answer here, I got negative 0.047, comma, positive 0.1754. So if you're going to type it in, you're going to have 0.2375 minus 0.1733, close, minus 1.96, big square root, fraction inside, 0.2375 times 0.7625 over 80. Go to the right, keep inside the square root, plus, oh, I didn't mean to write that. Okay, plus another fraction, 0.1733 times 0.8267. I'm sorry, I'm reading this out loud to you, over 150. There we go. That's my left. And then when you go up, this is what I was talking about before. Just be careful, backspace, or you could type it all in again, but I actually think backspacing is faster. The key is this guy is the one. It's the plus or minus z star. So this right here is what changes to plus. Boom. And that's your answer, 0.1754 right here. Now, what does this mean? Okay, well, you got to go back to your hypotheses. So our hypotheses were, and this is why I like the subtract, like equal 0, not equal to 0 part instead of this way. Because if you're doing an interval, this set of hypotheses is visually easier to figure out what you're going to do for here. We're testing, are they equal to 0? Is the difference equal to 0? Is the difference not equal to 0? So you have to ask yourself, is 0 in this interval? Yes, barely, but yes, it doesn't matter that it's barely. It does 0, right? So if you have a negative and you have a positive, then it's going to contain 0. So when I make my decision, I'm going to say since 0 is contained in the interval, do not reject the null hypothesis. We cannot conclude that there is a difference in proportions. Okay. All right, good job today. I hope you took really great notes. Make sure you jot down whatever questions you have so you can ask me and we can go through them together in school. Talk to you soon.